even and odd symmetry. A function f of x is said to have even symmetry if f of negative x equals f of x. That is the definition of even symmetry. Now, what does this mean graphically? Well, let's draw a graph of f of x. Let's draw a random graph. Of course, it's not going to be random. And let's think about the graph of f of negative x. Remember, when we're talking about transformations, that f of negative x will flip the graph over the y-axis. So what would happen if we flipped f of x over the y-axis? Do you see that we would get the exact same graph? So we say if a graph is symmetric with respect to the y-axis, then that graph has even symmetry. Now, how would we determine if something is even or has even symmetry? How will we determine that algebraically? Let's take a look at a couple examples that I know have even symmetry or that are even functions. Let's look at f of x equals x squared minus 3. To show that there is even symmetry, we need to find f of negative x and determine if this is the exact same thing that we started with. So f of negative x says for every x, we're going to replace it with negative x inside parentheses, giving us parentheses negative x all squared, then minus 3. And then if we simplify this, anything squared becomes positive, so we end up with x squared minus 3. And notice that this is exactly what we started with. It is the exact same thing as f of x. And that is the definition of even symmetry. How about another algebraic example? Let's look at g of x equals 7x squared minus x to the fourth plus the absolute value of x. To show that g has even symmetry, we need to start by finding g of negative x, which says for every x, we'll replace it inside parentheses with negative x. And then absolute values are just a fancy type of parentheses, so I'll just leave it as such. And then we simplify correctly, so anything squared becomes positive, then minus, right? The exponent comes before the multiplication of the negative 1. So I have negative x all to the fourth, which is positive x to the fourth, and then we still have this minus sign here. And then absolute value of anything just makes whatever I have positive. And notice that g of negative x is exactly the same as g of x. Since these two are the same, we have even symmetry. Let's take a look now at odd functions, or odd symmetry. So the definition of odd symmetry, or an odd function, is f of negative x equals not regular old f of x, but the negative of f of x. How would that work on a graph? Let's take a look at a graph that I know has odd symmetry. And that graph will be f of x equals x cubed. So how would we determine odd symmetry graphically? Well, there are really two things we need to see. I need to find f of negative x just like I did with odd symmetry. So f of negative x says let's flip the graph over the x-axis like this. Even though it's not dashed, I'm just drawing a dash to show you that this is not my original graph. And notice that f of negative x does not equal the original f of x. But it doesn't need to for odd. For odd symmetry, f of negative x needs to equal the negative of the original function. And the negative of the function is flipping over the x-axis. So this first one flipped over the y. And then the negative f of x flips over the x-axis. So if I were to flip my original function here over the x-axis, do you see how it would land exactly on my dashed line? So I'll fill that in now. That is, f of negative x equals negative f of x. That is odd symmetry graphically. And we say that an odd function is symmetric with respect to the origin. And so if you want to see it, if I were to take my original function, I'll try to get out as much of the new function as I can. And if you were to take the original graph, f of x, and rotate it 180 degrees, you would see that you get the exact same graph. That's why we call it symmetric with respect to the origin. So let's do some examples algebraically. I'm going to choose a couple functions that I know to be odd, or at least I hope to be odd. Let's take a look at h of x equals x cubed minus 2x. So recall that odd means h of negative x equals negative h of x, which means we really need to do a couple things. We need to find h of negative x, which says replace every x inside parentheses with a negative x. Now we'll simplify. A negative cubed is still negative. And now I have negative 2 times negative x, which gives me positive 2x. And notice that this does not equal the original function. It is not even. But I could also find the negative of h of x, which means I'll do negative. And now I'm going to substitute in h of x. And anytime we substitute in anything, we should substitute inside parentheses, which I will do there. And now I will distribute the negative sign, giving us negative x cubed plus 2x. Notice that h of negative x equals the negative of h of x. So this has odd symmetry. How about k of x equals x cubed over x squared plus 1? Does this have odd symmetry? Does it have even symmetry? Or maybe it has neither. Let's see. We'll start by finding k of negative x. We know what to do at this point. We'll substitute in and then simplify, giving us negative x cubed over positive x squared plus 1. So this does not equal the original, so it is not even. Let's try the negative of the original function. So we'll do negative. I'll just put it completely outside. And the negative of, inside parentheses, the entire function. The negative can go on top, on bottom, in the middle. It doesn't really matter, just so long as you put it only one time. So I'll put it on top. And notice this does equal k of negative x, which means this function is odd. Now, is there a quick way to find even, odd, or neither symmetry? Well, it depends. Let's do some examples. Are the functions even, odd, or neither? And all the functions I'm going to use here will be polynomials. So is there a shortcut for polynomials? And the answer is absolutely yes. Let's look at each of these individually. Starting with f of x. What do you think? Does the function f have even symmetry, odd symmetry, or neither? If you said neither, you would be correct. And the reason why is also why we call these even or odd symmetry, at least as far as I know. Notice that in my polynomial of f, I have both odd powers, a cubed, and then a first, as well as even powers, a squared, and then if I put an x to the 0, that's also even. Since we have both even and odd powers, I don't have even symmetry, I don't have odd symmetry, I have neither. So how about g of x? What kind of symmetry does this have? Well, since this is a polynomial with only odd powers, implied 1, given 3, given 5, only odd powers, it has odd symmetry. Finally, h of x has only even powers in my polynomial. I'll put the implied x to the 0 down here. So all my powers, 4, 2, 0, are even, which means the function has even symmetry. Note, this works for polynomials. It doesn't work for everything. It didn't work for this example when I did k of x. And it didn't work here because it's not a polynomial. But this little shortcut certainly works for polynomials.